So the last video, we went over how to test for relative max, relative mins, or saddle points of our given functions. Find the critical values and test. So this one we're going to basically do this. We're sort of putting all together everything we've done so far in 7.3. Alright, find critical values, determine if they are extreme or not using the d-test, show all work in your partial derivatives. Again, this is what you'd have to show on a test or a homework assignment. Alright, so first, find your critical values. Alright, so remember the critical values are when the first order derivatives equal 0 at the same time. Alright, so find the first order derivatives and set them equal to 0. So this is a simple case. There's only two x terms, so the derivative with respect to x, first order derivative with respect to x, is 24x minus 52. Set it equal to 0. Make sure you show that. That's a key step. So my rule of thumb is just to do it right away so you don't forget. You don't want to lose those points. And the first order derivative with respect to y, again, two y terms, so I get 60y minus 90. Set it equal to 0. I can only solve it when it's set equal to 0. Critical values are when both my functions equal 0. That's a key step. Everything I do from this point on is only true if I've set my derivatives equal to 0. Alright, so once I've done that, now I can solve. This one's a simple case, right? I've only got x terms and y terms in each, so solve accordingly. So 24x equals 52, divide by my 24. Alright, don't leave it 52 over 24. Also, don't give me a decimal approximation. You have a fraction key on your calculator. Give me it exactly what the x value is. So reduce it and give me that it's exactly 13 over 6. Alright, then do the same thing for y. Similar steps for y. Again, this one's a little easier to reduce. It reduces to 3/2. Alright, so my critical value is the point 13 over 6, 3/2. Alright, now I want to know, is that critical value a maximum, a minimum, or a saddle point? Alright, so now I do my d-test. So my d formula, which remember, is the second derivative with respect to x times the second derivative with respect to y minus one of my mixed derivatives squared. Which I'm just going to find, this one's actually a simple case, they're all going to be just numbers. Right, so if I take my second derivative with respect to x, so I'm looking here and taking the second derivative with respect to x. Actually, maybe I'll write them down. Second derivative with respect to x, so again I'm looking at this function, taking its derivative again with respect to x, well that's 24. Alright, then taking the derivative of that with respect to y, well there's no y value. Alright, so the second derivative with respect to y is 0. Alright, now I'm going to go over here and look at this function and take its derivative with respect to y. Alright, see y, which is 60. Alright, so all of my second derivatives came out numbers, right? Numerical values. And whenever it's a simple case like this, that will always happen. Right, now we plug, so these are the values, plug these into my d-test. Alright, so in this case, my d formula is just going to be making sure I multiply correctly. So it's going to be 24 times 60 minus 0 squared, which is a positive number. And so that just means my d came out positive. So yes, it's an extrema. And then I check my second derivative with respect to either one of them. Actually, they tell you the same thing. But our standard form is to use the x is 24. Always 24. So always positive, so that means it's always concave up. So yes, it's an extrema, it's concave up. And so that makes this a relative minimum. Alright, so I have a relative minimum at my critical value, which makes sense. If this is a cost function, more than likely we're looking for the absolute minimum cost. Well, that's what this would give me. This would give me my minimum cost. Alright, my next example. Alright, so same thing. Basically, put it all together. So find the critical values. Which means find my first order derivatives and set them equal to 0. So my first order derivatives in this case, with respect to x, so those are my 3x terms. So when I take my derivative with respect to x, I get negative 1200 x to the first plus 1200 y minus 300, set it equal to 0. Alright, my first order derivative with respect to y, so my y values. So negative 2400y plus 1200x plus 4500. Set it equal to 0. This is my linear case, which means I can use a matrix. Alright, before I get started, I have to write it in the form where I can plug it into my matrix, right, which is standard form. I get x value first, y value second, move my constant to the other side. So I'm going to write that down here. So I'm going to start with this function. And so in order to write it in the right well, x is in the right spot, y is in the right spot, but I have to add my 300 to the other side. Alright, so I'm going to get negative 1200x, 1200y equals positive 300 because I added it to the other side. Alright, now I'm looking here. I'm going to rearrange and make sure you're careful. It's really, if I'm going to do something silly, I'm going to forget to rearrange this and treat this as my x term, this is my y term. So make sure you're careful and you rearrange those. So the x value first, so it's 1200x first, minus the 2400y, equals, well, I got to move that 4500 to the other side. This time, when I move it to the other side, I have to subtract it. So I get a negative 4500. Alright, now I'm ready to go to my calculator and plug it into my calculator. Alright, I'm going to remind you again how to do that in case you've forgotten. Alright, so remember, a calculator has to be a 2 by 3. The x values first, then the y values. So my first equation is my first row in my matrix. My second equation is the second row in my matrix. Alright, so in your matrix key in your calculator, make sure it's a 2 by 3 size. Make sure you're careful and you plug them in that regard. So negative 1200, positive, there's a lot of 1200, so make sure you're careful. Negative 1200, positive 1200, 300, positive 1200, negative 2400, negative 4500. And then remember, you're going to go back into the matrix key on the calculator. You want to scroll down and find the double R, row reduced echelon form of the matrix you typed in. Hit enter and it should solve it for you, which should reduce it. Alright, remember the first number is your x value, the second number is your y value. And so this function has a critical point. .25 for the x, 3.5 for the y. And now we test to see if that critical point is a maximum, minimum, or saddle point. Alright, so that means I need my d-test. So I'm actually going to erase the work here that I did to solve for the critical value. So hopefully you have it, because I'm going to erase it. And then write my d-test formula here. I need my derivatives, my critical points. I'm going to leave those. Erase kind of all that work so I don't have to look at that. Alright. Now my test. So I need my d formula, which remember is the second derivative with respect to x, second derivative with respect to y, minus my mixed derivative squared. Don't forget to square it. Alright, I'm just going to find them and plug them into my formula. Whenever it's the linear case, these will always come out as single numerical values, alright, numbers. So I'm just going to plug them in when I find them. So I'm going to find the second derivative with respect to x. So I'm going to look here first. Second derivative here with respect to x, well, that's my only x term, so that's going to be negative 1200. Still going to look there, but now I'm going to find my mixed derivative. So looking here, taking the derivative with respect to y, well, with respect to y, that's a positive 1200. That goes there. All right, done with that one. That means now I'm going to look at the next one here. Alright, now I'm going to look at my y and take its derivative with respect to y. Well, there's the y part. So negative 2400. Alright, so there's my derivative, second derivatives. I just went ahead when I found them and plugged them straight into the D formula. Since the linear case, they're always going to come out numbers. Alright, and then you multiply them out. Alright, so when you multiply these out, it does come out positive. I actually think it's a fairly large number when you multiply them out. Yes, it is. Alright, it's a big positive number. So again, that just means yes, it's an extrema. Then I go look at the second derivative with respect to a single variable. So we pick xx. So xx was this one, which was negative 1200. Well, that came out negative, so that meant concave down in shape. And since it's concave down, that tells me this critical value has to be a relative maximum. Alright, so we find a relative maximum using our critical value. Again, it should make sense since it's a p of x. I'm going to guess it's standing for profit. So it should come out maximum because we usually want to maximize profit. Alright, the last one. Alright, so this is the last one for this set of notes. So this one, so we did a neither case, sorry, not a neither case. We did a case where each equation had just an x and a y. We did a linear case. Well, this one's going to be the substitution case. And I know that because of the cube term. Alright, find the criticals. Which means I find my first derivatives and set them equal to 0. Alright, so my first derivative with respect to x, 3 times 27 is 81. X to the second. Zero's away. Negative 72y. Zero's away. Set it equal to 0 so I don't forget. And now my first derivative with respect to y. So those are my y part. So 16y minus 72x. Set it equal to 0. Alright, so I've got the square here, which means I can't use a matrix. I have to use substitution. This is the easier equation, so this is the one I'm going to start with. The easier variable is y, because y is not being squared. So I'm going to solve this for y. Alright, so I'm going to take my 16y minus my 72x and solve for y. So I get 16y equals 72x, divide by my 16. And so y equals 4.5x. And so that's what we're going to use to substitute. Alright, so I'm going to replace my y with 4.5 times x. Alright, so that's my substitution step. So 81x squared minus 72 times 4.5x still equal to 0. And then that's the equation. So first thing I'm going to do is multiply out the 4.5 and 72. 81x squared minus 324x equals 0. Alright, and then it's a quadratic. This one's a simple case because there's no constant, so I can pull a factor out an x, so that's what I'm going to do. I'm going to pull an x out. I get 81x minus 324 still equal to 0, and now I set each of my factors to 0. So one of them is at 0, right? And the other one I have to do a little more work to solve. So 324 divided by 18 comes out 4. Alright, so I'm going to have two critical values. I'm going to plug in my x values here to find out what my y values are. So when I plug in 0 for x, I get out 0 for y. So there's one critical value, 0, 0. And then I'm going to plug 4 in here for x. So y is going to be whatever 4.5 times 4 is, which 4.5 times 4 is 18. Alright, so my critical values, I have two. My criticals are 0, 0, and 418. Alright, now I'm going to see if they are max, min, or saddle point. And I have to use my d-test. Alright, so now my d-test. So remember the d formula is find the second derivative with respect to x times the second derivative with respect to y minus the mixed derivative squared. And don't forget to square it. That one's easy to forget. Alright, so I'm going to go back up here And I'm going to find my second derivatives. I'm actually going to find them up here since this is where my first derivatives are. So I'm going to erase this to give myself room to write down my second derivatives. And then I'll plug them into my D formula. Alright, so my second derivative with respect to x, the mixed derivative, and my second derivative with respect to y. Alright, so with respect to x, it's x squared times 81. So that's going to come out 162x. And then my mixed derivative is the derivative of the negative 72y, so that's negative 72. Alright, so there's two of them. Now I go over here and find my last one. So the second derivative with respect to y is just 16. Right? I do have a variable part, so I'm going to go plug that into my D test. Alright, so my D test is going to come out 162x times negative 72 minus, or not negative 72. I need to go look before I go. My yy, which was 16, and then the negative 72 goes here for the mixed. All right. Now that I get all my numbers in the right place, right? My second derivative with respect to x was 162x. My second derivative with respect to y was 16, and my mixed derivative was negative 72. All right, I'm going to go ahead and simplify that. So 16 times 162, 2,592 times x, and then 72 squared is 5,184. All right, so there is my D equation. All right, now you test each one. So I'll start with 0, 0. So I'm going to take my 0, 0 and plug it in. All right, so 2,592 times 0, right, the x value is 0. That comes out negative 5,184 less than 0, so that tells me this is a saddle point. Alright, that's my test. Alright, now we're going to test the other point. Test 418. So I'm going to plug my 418 into my D formula. Really, I just need the 4. Right, because I only have an x term, so it's going to be 2,592 times 4 minus 5,184, and that comes out positive 5,184. So that checks off my D is positive. So yes, it's an extrema, and then I check the concavity. So my second derivative with respect to x was the 162x. When I plug in my point, which would be the 4 value for x, I get 162 times 4, which is going to come out positive, so that tells me it's concave up. Alright, so it's concave up, it's an extrema, and so that tells me that this is a relative minimum. Right, and that's the test, the reason why. Alright, so that finishes up this set of notes. So finding critical values and testing them. Alright, so this is the, if you're looking at the handouts, this is the finished, the 7.3 part 1 handout. Next will be the 7.3 part 2, which are then applications. So we're going to be finding these critical values and determining if they're max and mins in application type problems. So that's the next set of notes, applying it. All right, we'll stop there.